Hello everyone, welcome to today's lecture. In this lecture, we are going to learn about the third error detection technique, which is a cyclic redundancy check. So this method is very useful nowadays, mostly for any communication. The error detection technique used is a cyclic redundancy check. So it is a most powerful and easy to implement technique. And it is a binary division technique, like we are using the binary numbers and binary division for finding the errors. So in CRC, a sequence of redundant bits are appended to the end of the data units so that the resulting data unit become exactly divisible by a second and predetermined by a binary numbers. So exactly what we are doing now, suppose this is a data segment and we apply the CRC, means the cyclic redundancy check encoder at the sender side. So what happened at the sender side? We are adding some redundant bits with the original message bits. Suppose our message is hi, so we are converting this message into the binary bits, and then we'll attach some CRC bits, or it is also called the redundant bits, at the end of that message, and then we'll send that message over the computer network. And suppose the message is corrupted while transmission, so at the receiver side there are another CRC decoder is there. So at the CRC decoder some binary division is happen, and at the end if remainder of the division is 0, then the data segment is not corrupted, and if its remainder is 0, if its remainder is not a 0 number, then we can say that it is a corrupted message. So this is how the error is calculated in the cyclic redundancy check. So at the destination, the incoming data unit is divided by the same numbers. If at this step there is no remainder, the data unit is assumed to be correct and is therefore accepted, as I said that. And a remainder indicates that the data unit has been damaged in transit and therefore must be rejected. So the binary number, which is r+1 bits in length, can also be considered as a coefficient of polynomial called generator polynomial. So in that also we are using some polynomial equations for finding the CRC bits. So now first let's understand how the process is worked. As I said that first, suppose some of the message bits are here and we are adding some redundant bits as a CRC bit at the end of the data, and now this m+n bit is given to the CRC encoder, and now that CRC encoder sends data to the receiver. At the receiver side, that CRC decoder works, and after division, if remainder is 0 and it is yes, then accept that message bit and otherwise reject it. So that is how the process is worked. CRC is a very effective error detection technique. If the divisor is chosen according to the previously mentioned rule, its performance can be summarized as follow, like it can detect a single bit error, double bit error, odd numbers errors. CRC bit can detect all burst errors of less than a degree of polynomial. Yes, so it can detect any type of errors. Suppose these are the polynomial equations, and if its power is 8, so up to the 8 polynomial bits it can detect the errors. So these are the some standard polynomial equations that is used for CRC, and it is also used in some ATM, yes, LAN. So for that different polynomial equation is there. Now let's understand what are the advantages and disadvantages of this method. So easily implemented method in any hardware and software. Cyclic codes are faster when implemented in hardware, and it gives a good performance in detecting a single bit error and odd numbers of errors and burst errors. When some disadvantages are CRC is not suitable for protecting against intentional alterations of data. an overflow of data is possible in CRC. So suppose we want to update that intentionally, then it is not suitable. So that is the disadvantage. Now let's understand how CRC works with some example. Suppose here generate the CRC code for message. So this is a message bits 100100. So these are the message bits, and some given a generator polynomial equation is already given here. So now based on this polynomial equation and based on this message bit, we need to generate the CRC bits. Yes, now we have message 100100, but at the receiver side we are sending M plus N bits. N bits means a CRC bits. We are adding the redundant bits at the end of the message. So for that we need to generate the CRC code, that which bits we are generating, sorry, which bits we are adding at the end of the message, so that we need to calculate. So we can calculate it by this method. So let's understand. Suppose our message bit is 1 0 0 1 0 0. Okay, so this is the message bit, and now we need to append this message. So for that we need to consider this polynomial equation, which is x raised to 3 plus x raised to 2 plus 1. So we can write this equation is something like that. The coefficient is 1, so 1 into x raised to 3 plus 1 into x raised to 2 plus, because x raised to 1 is not there, so the coefficient is 0, so 0 into x raised to 1 plus the last one is a 1, so the coefficient is x raised to 0. So from that we can generate one message series. So by considering only coefficient value 1 1 0 and 1, so by considering only that value we can generate some numbers from this equation. So this is the number and this is a divisor. We are using this as a divisor. So we are for finding the CRC code we are doing the division, and because now our generated number is of 4 bits 1 2 3 and 4, so the number of 0 we are appending at the end of the message is g of x, number of bits in g of x minus 1. So here the number of bits is 4 minus 1, so number of bits become 3. So here we are adding 1 2 and 3 0, and we are doing the division. So here we are appending the 3 different zeros at the end of the message bits, or we can consider maximum power number equals to 3, so that is why we are appending the 3 bits 3 0 at the end of the message string. Now we'll do the division. Now we already know this is a divisor. 1 1 0 1 is a divisor, and the message bit is become 1 0 0 1 0 0 0 0. So 1 0 0 1 0 0 0 0, and divisor is 1 1 0 1. Now we'll start the division. So let's multiply this with 1, so it becomes 1 1 0 1. Now we'll apply the XOR operation. So 1 1 becomes 0, 0 1 means 1. XOR means if both numbers are same, then it equals to 0, and if both numbers are different, then it equals to 1. So because 0 1 1 0 0 0 1 1 0. Now we'll again do this. So for that we here only 3 bits, and in our divisor there are 4 bits, so we are taking 1 bit from upper level. So here the bit is become 1 0 0 0, and our divisor is 1 1 0 1. So it's 1 1 0 0 1 1 0 0 0 0 1 1, and again we'll take the another 0 from above. So now again we'll use our divisor. So So that is how the whole process is working, and at the end we'll get the reminder 001. So these are the 3 bits that we need to use. And suppose here we are writing the 0 here, so this become a 4 bits, but we are considering the 3 bits because our highest power is 3, so we are only considering 3 bits from LSB. So 001 equals, these are the 3 bits that we are appending with our message. So our message is 100 100, and we are appending 001, that is this 3 bits. We are appending this with our message, so our message has become 100 100, and this 3 bits is 001. So now this message is ready for send. Now this message is sent over the network and received at the receiver side. Now at the receiver side, again it calculate the reminder. So our message is 100 100 001. These are the CRC bits, and divisor is 1101. Whole process again repeated, and at the end now we can see that the reminder is 0. If reminder value is 0, then the number of bits sent is original. There is no bits are corrupted or no bits are changed. So in that case only the reminder is become 0 and our data is saved. Suppose we are changing bits here 0 to 1 and 1 to 0. So at that situation the results at that situation the remainder can't be 0. If we are changing any bits in our data, then the remainder value doesn't become 0. So we can easily identify that our message is corrupted or not. So that is how we can calculate the errors by using the cyclic redundancy check. This is another example. Suppose this is a message bits. Here the polynomial value is x raised to 4 into x square plus 1. So from that we will generate a 101 divisor, and we are adding, because the maximum power is 4, so we are adding 40 at the message, and then we'll calculate the division with this divisor, and at the end will reminder is become 0110. You can calculate this example by yourself, and you can generate the answer. So in your answer the reminder is 0110. So now we'll attach this reminder value at the end of our message, and now this whole message is ready for send. And same as if at the receiver side we are doing the division and the remainder becomes 0. So that is how cyclic redundancy check is used. That's it. Thank you so much for listening.